Okay, so in the previous technique, subsystem hazard analysis was in the detailed design phase of the system life cycle, and that focused on the trees to the exclusion of the forest. We weren't looking for the forest, we were looking into the depths, the detail, the trees. This system hazard analysis, this one we're going to talk about now, moves back up in altitude just a little bit. It looks more at the forest rather than the trees. The objective of the system hazard analysis is to identify hazards at the system level, to evaluate subsystem interrelationships or interfaces, and to evaluate safety compliance at the system level. So we're looking at the system level. While this analysis is a higher system level technique, though, supplemental techniques can be used when necessary to drill down into safety critical functions and top level mishaps that the engineer feels are warranted. We're still in the development phase of the system life cycle, but we're more advanced into the system. The system level analysis often starts concurrently with the subsystem analysis. However, it continues longer than on longer into the production, sometimes even into the operation phases. The the system hazard analysis (SHA) is not a continuation of the subsystem hazard analysis, though. This slide may make it look that way. I know we have said that the PHL flows to the PHA flows on in, but in this case, the outputs of the subsystem hazard analysis are not inputs to the system hazard analysis. The systems hazard analysis starts at a different point. It starts with top-level mishaps and safety-critical functions. Hazards identified in the subsystem hazard analysis, they have been analyzed to enough detail already. So we're going to start at a different level here in the SHA. So the SHA does, though, receive input from hazard analysis techniques performed thus far. So all of them do actually provide some input, but the input that they provide is the condensed top-level mishaps and safety-critical functions. So that said, the success of the system hazard analysis depends greatly upon how the quality of the other previous techniques, upon the quality of how they were conducted. So that can be illustrated by this slide. Look at the inputs to the system design hazard analysis type. Look at all the inputs. We've got one coming from the detailed design, we've got one coming from requirements design, we've got an input coming from operational design, coming from human design. So the inputs into the system level hazard analysis type come from detailed design, requirements design, human design, operational design. The system hazard analysis churns up all those results that are gathered from all the other analysis types and puts out integrated system hazards, top-level mishaps, and risk to help continue to enhance the system design for safety. The system hazard analysis begins with top-level mishaps and safety-critical functions. Those have been identified in previous hazard analysis techniques. So please note, if it has not been already done, you should make sure that all the hazards listed in previous techniques are combined under identified top-level mishaps. No identified hazards should be left out hanging. From our example in the text, we boiled down all of the identified hazards in the ACE missile system to these top-level mishaps, if you remember from Table 8.2. 9 of those top-level mishaps were identified during the preliminary hazard analysis phase, and one additional top-level mishap, a 10th one, was identified during the subsystem hazard analysis. So those top 10 things are what goes into the TLM/SCF column of the system hazard analysis worksheet. So you have from table 10.2, you have the ACE missile system top-level mishaps. This came from the subsystem hazard analysis. So all those hazards were boiled down and identified these top 10 these 10 top-level mishaps. And you can see how they have been transferred from this list into the system hazard analysis worksheet. Let's talk for just a moment about the relationship between top-level mishap and safety critical function. There's a relationship there. We already discussed what safety critical means. It means the results are catastrophic or critical if things go bad. If it goes bad, the consequence is catastrophic or critical. A safety critical function is something that has to go right, or catastrophic or critical consequences might result. If the safety critical function does not function properly, it results in a top-level mishap. A car, for example, must steer properly in order not to crash into a tree. If the steering fails, the car may crash into a tree. The top-level mishap and safety critical function are often just mirrors or inverse of each other. The safety critical function is what must happen successfully for things to go right. The top-level mishap is what happens if it goes wrong. Safety critical function threads can be useful to help us see subsystem interfaces. For an aircraft landing gear, the landing gear down switch must tell the hydraulic motor, the electric motor, to start pumping hydraulic fluid one direction or another, and that has to pump hydraulic pressure through the actuators. The gear doors must open and close appropriately as the gear raises and lowers, and the whole system must stop operation once the electrical limit switches have been reached. So all of those subsystems and functions line up to actuate the safety critical function, SCF, of raising and lowering the landing gear. Through that, we can identify where system interfaces may cause hazards. In our landing gear example, what if the pump motor is pumping the gear up and the doors do not actuate properly? The gear keeps swinging, say, damaging both the gear and the doors, jamming the gear in an intermediate spot. It's a safety hazard. That's a safety critical function. We can do a safety critical function thread to help picture that. Make sure that we don't have interface hazards. This is a safety critical function thread from our text. What things should happen in order, and if one of those functions do not interface properly, we can see what type of hazard might be. The last point that I want to bring out on the on the system hazard analysis is that the recommended action is becoming more and more critical to our analysis. The recommended action column is helping us to generate system safety requirements that will be put into place to help mitigate risk and make our system as safe as it can be.